When you look up at the night sky and see that faint red dot hanging in the darkness, you're staring at what might be the greatest mystery in our solar system. Not because Mars is empty and lifeless, but because it might once have been anything but empty. What if everything we think we know about the story of intelligence in our cosmic neighborhood is backwards? What if Earth wasn't the first world to develop advanced civilizations, but simply the second act in a much older drama? Tonight, we're going to explore a possibility that challenges everything you've been taught about the history of life and intelligence in our solar system. We're going to ask whether Mars, that cold and seemingly barren world, might have once been home to civilizations that rose and fell millions or even billions of years before the first human ever drew breath on Earth. Now, before you click away thinking this is just another science fiction fantasy, let me be clear about what we're dealing with here. This isn't about little green men or flying saucers. This is about legitimate scientific questions that researchers are beginning to ask more seriously. Questions about deep time, planetary evolution, and the possibility that intelligence might be far less rare than we assume. Questions that, if answered differently than we expect, would fundamentally rewrite our understanding of where we come from and whether we're truly alone. Here's what we know for certain. Mars is old, really old. It formed roughly the same time as Earth, about 4.5 billion years ago. But unlike Earth, which took its time developing stable conditions for complex life, Mars may have been habitable much earlier in its history. While our planet was still a molten hellscape being bombarded by asteroids, Mars might already have had oceans, rivers, and the kind of stable climate that could support not just life, but the long evolutionary timescales needed for intelligence to emerge. Think about that timeline for a moment. If Mars became habitable even a few 100 million years before Earth, that represents an enormous head start. On Earth, it took roughly 3.5 billion years for life to evolve from simple bacteria to complex multicellular organisms. It took another 500 million years to get from the first complex animals to the first humans. But what could happen in that same time span in a world that got started earlier? The evidence is starting to pile up that Mars wasn't always the frozen desert we see today. Satellite images show dried riverbeds carved into the Martian surface. We can see what appear to be ancient shorelines marking where vast oceans once lapped against continents. The chemistry of Martian soil tells us about long periods of flowing water and stable weather patterns. All the ingredients for a living world were there, and they were there early. But here's where it gets really interesting. We're not just talking about microbial life or simple plants and animals. We're talking about the possibility that Mars had enough time and the right conditions for evolution to take the same path it eventually took on Earth. The path toward intelligence, toward civilization, toward species capable of shaping their environment and asking questions about their place in the universe. Now I know what you're thinking. Where are the ruins? Where are the artifacts? Where are the massive stone monuments or metal cities that should have survived if an advanced civilization really existed on Mars? And that's exactly the right question to ask, because it gets to the heart of why this possibility is so fascinating and so difficult to prove or disprove. The answer lies in something that most people don't fully appreciate about planetary geology. Earth is incredibly good at erasing its own history. Plate tectonics constantly recycle the surface, pushing old rocks down into the mantle and bringing new material up from below. Erosion wears down mountains and fills in valleys. Weather breaks apart even the strongest materials over long periods of time. Here on Earth, we can barely find traces of human civilization that are more than a few thousand years old. The oldest human structures are already crumbling ruins. Give it 1,000,000 years and almost nothing we've built will remain recognizable. Give it 100 million years and future archaeologists might find only the faintest chemical traces that we were ever here at all. Now imagine that same process operating not for thousands or millions of years, but for billions. Imagine the kind of geological recycling and atmospheric erosion that could completely erase even the most massive construction projects. Mars may not have active plate tectonics like Earth, but it has its own ways of burying the past. Dust storms that can engulf the entire planet, impact craters from asteroid strikes, volcanic activity that was once far more intense than anything Earth has experienced. If a civilization existed on Mars 2 billion years ago, or even 500 million years ago, we might not expect to find obvious ruins. Instead, we might have to look for much subtler clues: chemical signatures in rock layers, unusual mineral concentrations, isotope ratios that don't quite match what we'd expect from purely natural processes. And here's the thing that makes this more than just wild speculation. We're starting to find exactly those kinds of anomalies. Not smoking gun proof of ancient Martian cities, but puzzling data points that don't fit neatly into our models of how planets should evolve naturally. Take the atmosphere of Mars, for example. The ratios of different gases and isotopes don't quite match what we'd predict from standard planetary formation models. There are signatures that some scientists have suggested could indicate massive industrial activity in the distant past. Rapid changes in atmospheric composition that happened too quickly to be explained by gradual geological processes alone. Or consider the strange spherical formations found scattered across the Martian surface. These perfectly round objects, some metallic, some mineral, appear in rock layers that are incredibly ancient. Most are explained as natural formations, the result of chemical processes we don't fully understand, but their geometric perfection and widespread distribution have raised questions about whether all of them can be accounted for by natural causes. Then there are the more controversial findings. Researchers analyzing high-resolution images of the Martian surface have identified formations that appear almost architectural, straight lines where nature typically creates curves, right angles where erosion usually produces gentle slopes, patterns of organization that seem too regular to be purely coincidental. The scientific mainstream treats these observations with appropriate skepticism. Extraordinary claims require extraordinary evidence, and we're nowhere near that threshold yet. The human brain is remarkably good at seeing patterns where none exist, especially when we're looking at grainy images from millions of miles away. But that skepticism, while necessary, shouldn't blind us to the possibility that we're missing something important. Science progresses by asking uncomfortable questions and following the evidence wherever it leads, even when it challenges our assumptions about how the universe works. The more we learn about Mars, the more we realize how Earth-like it once was. The more Earth-like it was, the more reasonable it becomes to ask whether evolution might have followed similar paths on both worlds. And if evolution did follow similar paths, then the emergence of intelligence becomes not just possible, but almost inevitable given enough time. This brings us to one of the most profound questions in astrobiology. Is intelligence rare or common? Are we the result of a 1,000,000,000-to-1 cosmic accident? Or are we the natural outcome of processes that happen wherever conditions are right? The answer to that question depends partly on whether intelligence has emerged before in our own solar system. If Mars really did host advanced civilizations in its distant past, it would suggest that intelligence is not nearly as rare as we often assume. It would mean that, given the right conditions and enough time, evolution tends toward complexity, toward awareness, toward civilizations capable of contemplating their own existence. But it would also raise darker questions about the fate of those civilizations, because whatever intelligence might have arisen on Mars, it's clearly not there anymore. The red planet today is silent, cold, and apparently lifeless. If civilizations did once flourish there, something ended them. Was it environmental collapse as the planet's atmosphere gradually leaked away into space? Was it self-destruction through war or ecological disaster? Or was it something more subtle, a gradual decline? As resources dwindled and populations couldn't sustain the complex technologies needed for civilization, understanding what happened to hypothetical Martian civilizations might give us crucial insights into our own future. Are there universal patterns in how intelligent species develop and decline? Are there warning signs we should be watching for? Are there paths towards sustainability that we haven't yet discovered? These questions become even more urgent when we consider the possibility that life on Earth and Mars might be more connected than we realize. Scientists have long known that rocks can be blasted off one planet by asteroid impacts and eventually land on another. We've actually found meteorites on Earth that originated on Mars. If life existed on Mars when these exchanges were happening, it's possible that biological material, maybe even complex organisms, could have traveled between the two worlds. The early history of life on Earth might have been seeded or influenced by whatever was happening on Mars at the same time. This opens up the almost science fiction possibility that we ourselves might be the distant descendants of Martian life, that our own evolutionary tree might have roots that stretch back not just to early Earth, but to an even earlier Mars, where life had already learned to thrive and adapt and eventually think. If that's true, then our search for evidence of ancient Martian civilizations isn't just about understanding another world. It's about understanding ourselves, our origins, and our place in a story that might be far older and more complex than we've ever imagined. The implications of this possibility extend far beyond academic curiosity. If Mars once hosted intelligent life, it forces us to reconsider some of our most basic assumptions about how civilizations develop and what causes them to disappear. Because here's the uncomfortable truth that we need to face. Whatever might have happened on Mars, it ended. The silence we see today across that rust-colored landscape isn't the silence of a world that never knew intelligence. It might be the silence that comes after intelligence has run its course. This raises questions that hit uncomfortably close to home. If Martian civilizations did exist and then vanish, what does that tell us about the sustainability of technological societies? Are there universal patterns that govern how intelligent species interact with their environments? Are there thresholds that, once crossed, lead inevitably to decline? The more we study Mars, the more we see a world that seems to have experienced exactly the kind of environmental catastrophe that many scientists worry could be in Earth's future. The planet appears to have lost most of its atmosphere over geological time, transforming from a warm, wet world capable of supporting complex ecosystems into the frozen desert we observe today. But what if that transformation wasn't entirely natural? What if it was accelerated or even caused by the activities of the very civilizations it might have supported? The atmospheric chemistry of Mars shows signs of rapid, dramatic changes that are difficult to explain through geological processes alone. Could these be the signatures of industrial activity on a planetary scale? Could we be looking at the aftermath of a civilization that altered its environment so dramatically that it couldn't survive the consequences? These aren't just abstract philosophical questions. They're practical concerns for our own species as we face our own environmental challenges. If Mars really did experience civilizational collapse tied to environmental degradation, then studying what happened there becomes crucial for understanding what we need to avoid here on Earth. The search for evidence of ancient Martian intelligence is becoming more sophisticated as our technology improves. Future missions to Mars will carry instruments specifically designed to look for the kinds of subtle chemical and geological signatures that might remain from industrial activity billions of years in the past. We're developing techniques to analyze isotope ratios, mineral concentrations, and atmospheric chemistry with unprecedented precision. But even as our methods improve, we have to acknowledge the limitations of what we're likely to find. If civilizations existed on Mars in the deep past, they would have had billions of years to be erased by natural processes. The evidence we're looking for might be so faint, so degraded, that it's barely distinguishable from the background noise of normal planetary evolution. This creates a frustrating situation for researchers. The absence of obvious evidence doesn't prove that ancient civilizations never existed on Mars. It might simply reflect the thoroughness with which time erases even the most impressive achievements of intelligent species. We could be looking at a world that once hosted cities, art, science, philosophy, and technology, but now shows only the faintest chemical echoes of that lost greatness. The possibility becomes even more intriguing when we consider what we know about the timing of planetary evolution in our solar system. Mars reached habitability earlier than Earth, but it also began losing its ability to support complex life much earlier. This creates a window, possibly lasting hundreds of millions of years, during which Mars could have supported the long evolutionary timescales needed for intelligence to emerge, while Earth was still uninhabitable. During this window, any civilizations that arose on Mars would have had the solar system essentially to themselves. They would have looked out at the other planets and seen worlds that were either too hot, too cold, or too unstable to support life as they knew it. Earth, in particular, would have appeared as a promising but not yet ready neighbour, a world that might someday become habitable, but wasn't there yet. This timeline opens up possibilities that sound like science fiction, but are grounded in legitimate scientific speculation. Could ancient Martian civilizations have monitored Earth's development? Could they have recognized its potential and perhaps even taken steps to influence its evolution? Could the emergence of life on Earth have been guided or accelerated by intelligence that originated on Mars? The panspermia hypothesis, which suggests that life can spread between planets through natural processes, becomes even more intriguing when we consider the possibility of directed panspermia. Instead of random rocks carrying microbes between worlds, we might be looking at deliberate seeding of one planet by intelligence from another. If this sounds too fantastic to take seriously, consider what our own species is already planning. We're actively discussing missions to terraform Mars, to seed it with Earth life, to create backup colonies for human civilization. If we can contemplate such projects with our current primitive technology, what might a civilization with millions of years of additional development have been capable of? But this raises another uncomfortable possibility. If Martian civilizations were advanced enough to influence the development of life on other worlds, why didn't they simply migrate to Earth when Mars began to become uninhabitable? Why didn't they establish colonies here that could have survived the environmental collapse of their home world? Perhaps they did try. Perhaps the reason we find life on Earth appearing so quickly after the planet became habitable is that it didn't evolve here from scratch. Perhaps it arrived as refugees from a dying Mars, carrying within its genetic code the memory of civilizations that no longer exist. Or perhaps the civilizations of Mars made a different choice entirely. Perhaps they recognized that their time was ending and chose to face extinction with dignity rather than abandoning their home world. Perhaps they decided that their legacy would live on not in colonies or monuments, but in the life they helped to flourish on the blue planet next door. This possibility transforms our entire understanding of what it means to be human. Instead of seeing ourselves as the first intelligence to arise in our solar system, we might be the inheritors of a much older tradition. The curiosity that drives us to explore space, the creativity that leads us to art and science, the restless energy that pushes us to ask questions about our place in the universe. All of these might be echoes of characteristics that first emerged under alien skies on a world that is now silent. The search for ancient Martian civilizations is really a search for our own deeper history. Every rock sample we analyze, every atmospheric measurement we take, every high-resolution image we study is potentially a piece of a puzzle that could reveal not just what happened on Mars, but what we ourselves might become. Because if Mars really did host advanced civilizations that eventually vanished, then we're looking at both a warning and an inspiration. A warning about the fragility of even the most advanced societies, and an inspiration about the power of intelligence to create meaning and beauty, even in the face of inevitable extinction. The red dot in our night sky might not be just another planet. It might be a monument to possibilities we're only beginning to understand, a reminder that intelligence and civilization might be far more common in the universe than we dare to hope, and far more precious because of how easily they can be lost. The story becomes even more compelling when we consider the mechanics of how such evidence might survive across geological time. While massive structures and obvious artifacts would likely be erased by billions of years of erosion and planetary recycling, certain signatures could persist in ways that are almost impossible to destroy completely. Consider the carbon cycle, for instance. Every industrial civilization leaves a distinctive fingerprint in the atmospheric chemistry of its planet. When we burn fossil fuels, we release carbon that has been locked away for millions of years, creating specific isotopic signatures that can be detected in ice cores, sediment layers, and even in the shells of marine organisms. These signatures don't just disappear when a civilization ends. They get locked into the geological record, preserved in rock layers like pages in an ancient book. On Earth, we can already see the chemical signature of our own industrial age beginning to appear in geological formations. Future scientists studying our planet millions of years from now would be able to detect the sudden spike in atmospheric carbon dioxide that began in the 1800s, even if every trace of our cities and technology had long since crumbled to dust. If Mars once hosted industrial civilizations, similar signatures might still exist in its geological record. The challenge is that Mars has a much more dynamic atmospheric history than Earth. Its thinner atmosphere and lack of a strong magnetic field mean that much of its early atmospheric history has been literally blown away into space by solar wind. But not all of it. Enough might remain, locked in mineral deposits and sediment layers, to tell the story of what once was. Recent analysis of Martian meteorites found on Earth has revealed some intriguing anomalies. Certain isotope ratios that don't quite match what we would expect from purely natural processes. Concentrations of rare elements that seem unusually high for a planet that supposedly never experienced industrial activity. These findings are still highly controversial and have alternative explanations, but they represent exactly the kind of subtle evidence we might expect to find if ancient civilizations once altered the chemistry of the Martian environment. The timing of these anomalies is particularly interesting. Many appear to date from periods when Mars was transitioning from its early, more habitable phase to its current frozen state. This would be exactly when we might expect civilizations to have emerged, flourished, and then faced the ultimate environmental challenge as their planet slowly became uninhabitable. But chemical signatures are just one piece of the puzzle. There are also physical structures on Mars that continue to defy easy explanation. The famous face on Mars, photographed by Viking missions in the 1970s, turned out to be a natural rock formation when viewed at higher resolution. But it wasn't the only unusual feature discovered by our robotic explorers. Across the Martian landscape, there are formations that display geometric regularity that seem almost too perfect to be entirely natural. Straight lines stretching for kilometers across terrain where wind and water erosion should have created more irregular patterns. Circular formations arranged in patterns that suggest deliberate placement rather than random geological processes. Rectangular depressions that look almost like the foundations of massive structures, now buried under millions of years of sediment. The scientific consensus is that these features have natural explanations. Mars has unique geological processes that can create surprisingly regular formations. The planet's different gravitational field, atmospheric pressure, and chemical composition can lead to erosion patterns and mineral deposits that don't have exact analogues on Earth. What looks artificial to our Earth-trained eyes might simply be the result of Martian geology operating according to its own rules. But the sheer number of these anomalous formations is starting to raise questions even among skeptical scientists. While any individual feature can be explained by natural processes, the statistical probability of so many regular geometric formations arising purely by chance is becoming increasingly difficult to dismiss. This is where the search for ancient Martian intelligence enters truly fascinating territory. Instead of looking for obvious artifacts or ruins, researchers are beginning to apply statistical analysis to the distribution of unusual features across the Martian surface. They're asking whether patterns of organization exist that would be extremely unlikely to arise from natural processes alone. Early results from this kind of analysis are intriguing but far from conclusive. There do appear to be correlations between certain types of geometric formations and specific geological regions that suggest non-random processes at work. But correlation isn't causation, and the challenge remains to distinguish between unknown natural processes and possible evidence of ancient intelligence. The search is complicated by the fact that we're essentially trying to reconstruct a crime scene that's billions of years old. Every piece of potential evidence has been subjected to eons of contamination, degradation, and natural recycling. It's like trying to solve a murder mystery where the scene has been cleaned, repainted, and renovated countless times over geological timescales. This is why the most promising avenue for finding evidence of ancient Martian civilizations might not be on Mars itself, but in the rocks from Mars that have naturally traveled to Earth. Martian meteorites represent samples of the red planet that have been preserved in the cold vacuum of space for millions of years, protected from the ongoing geological processes that might have erased evidence on the planet's surface. Scientists have identified dozens of meteorites that definitely originated on Mars, blasted into space by asteroid impacts and eventually captured by Earth's gravity. These rocks provide a unique window into Mars's deep history, and some contain features that continue to puzzle researchers. The most famous example is the Allen Hills meteorite, designated ALH 4001, which was found in Antarctica in 1984. This ancient rock, formed on Mars over 4 billion years ago, contains microscopic structures that some scientists interpret as fossilized bacteria. The debate over these supposed Martian microfossils has raged for decades, with experts divided over whether they represent genuine evidence of ancient life or simply unusual mineral formations. But ALH 4001 also contains other anomalies that have received less public attention but might be even more significant. Unusual magnetic properties that suggest the rock was formed in the presence of a strong magnetic field, much stronger than Mars currently possesses. Isotopic signatures that don't match current models of Martian atmospheric evolution. Trace element concentrations that seem to require chemical processes more complex than simple volcanic activity. Individually, each of these anomalies can be explained by natural processes we don't fully understand. But taken together, they paint a picture of a Mars that was far more geologically and potentially biologically active than our current models predict. They suggest a planet that experienced rapid, dramatic changes in ways that are difficult to account for through gradual evolutionary processes alone. The implications become even more intriguing when we consider what we know about the history of intelligence on Earth. The fossil record shows that complex life remained relatively simple for billions of years, then suddenly exploded into incredible diversity during what's known as the Cambrian explosion, roughly 540 million years ago. The triggers for this sudden burst of evolutionary innovation are still hotly debated among scientists. Could the Cambrian explosion have been influenced by genetic material arriving from Mars during a period when that planet was experiencing its own evolutionary crisis? Could dying Martian ecosystems have inadvertently seeded Earth with the biological innovations that led to the rapid diversification of complex life? This idea might sound far-fetched, but it's based on solid, scientific principles. We know that rocks regularly travel between Mars and Earth. We know that microorganisms can survive in space for extended periods under the right conditions. We know that horizontal gene transfer, the movement of genetic material between different species, has played a crucial role in evolution throughout Earth's history. If Mars was experiencing a period of intense evolutionary pressure as its environment became increasingly hostile, its organisms might have developed biological innovations at an accelerated pace. Some of these innovations could have been preserved in Martian rocks that were subsequently blasted into space and eventually delivered to Earth, where they could have been incorporated into terrestrial ecosystems through natural genetic exchange processes. This scenario would help explain some of the puzzling aspects of the Cambrian explosion, particularly the sudden appearance of complex biological structures that seem to require numerous coordinated genetic changes. Instead of these innovations arising independently on Earth, they might represent the importation of evolutionary solutions that had already been developed on Mars under different environmental pressures. The possibility becomes even more intriguing when we consider the timeline involved. The Cambrian explosion occurred roughly 540 million years ago, during a period when Mars was transitioning from its early habitable phase to its current frozen state. This would have been exactly when Martian life forms would have been under maximum evolutionary pressure to develop new survival strategies. Could the burst of biological innovation that transformed Earth's biosphere have been the final legacy of a dying Martian ecosystem? Could the complexity and intelligence that eventually led to human civilization have roots that extend back to evolutionary experiments conducted under alien skies. These questions push the boundaries between legitimate scientific speculation and science fiction, but they're grounded in real phenomena and observable processes. The exchange of material between planets is not just theoretical, it's documented fact. The survival of organisms in space is not just possible, it's been experimentally verified. The role of horizontal gene transfer in evolution is not controversial, it's fundamental to our understanding of how life develops and adapts. What remains uncertain is the scale and significance of these processes in the deep history of our solar system. But as our techniques for analyzing ancient materials become more sophisticated, and as we gather more samples from Mars through robotic missions, we may finally be able to answer some of these profound questions about the interconnected history of life on two worlds. The search for ancient Martian civilizations is ultimately a search for understanding our place in a cosmic story that might be far more complex and interconnected than we've ever imagined. Every new piece of evidence, every refined analysis, every unexpected discovery brings us closer to answering one of the most fundamental questions we can ask. Are we alone, or are we part of a legacy that stretches back through deep time to the earliest days of intelligence in our solar system? The possibility that we might be inheritors of an ancient Martian legacy raises questions that go far beyond simple archaeology or paleontology. We're talking about rewriting the fundamental narrative of intelligence itself. If Mars really did host advanced civilizations before Earth became habitable, then consciousness and technology aren't rare cosmic accidents. They're recurring themes in planetary evolution, patterns that emerge whenever the right conditions persist for long enough. This perspective transforms how we think about our own future. Instead of seeing human civilization as a unique experiment with an uncertain outcome, we might be looking at one iteration of a much older process. Intelligence emerges, faces challenges, adapts or fails, and leaves traces for the next iteration to discover and learn from. Mars becomes not just another planet, but a laboratory where the fundamental questions of civilization were first explored. The evidence we're gathering from Mars continues to complicate our understanding of what a habitable planet should look like. Traditional models suggested that Mars lost its atmosphere and water gradually over hundreds of millions of years through well-understood physical processes. Solar winds stripped away the thin atmosphere. Lower gravity couldn't hold onto water vapor. Volcanic activity declined, reducing the greenhouse gases needed to maintain surface temperatures. But new data is revealing a more complex story. The transition from habitable Mars to frozen Mars appears to have happened much more rapidly than these gradual processes would suggest. Isotopic evidence points to sudden dramatic changes in atmospheric composition. Geological formations suggest catastrophic flooding events, followed by equally sudden drying. The planet seems to have experienced rapid environmental shifts that are difficult to explain through natural causes alone. Could these rapid changes be signatures of civilizational activity? Industrial processes operating on a planetary scale? Geoengineering projects that succeeded too well or failed catastrophically? The chemical fingerprints we're finding in Martian samples don't rule out these possibilities. In fact, some of the anomalies would be easier to explain if they resulted from intentional atmospheric manipulation rather than purely natural processes. Consider what our own civilization is already planning for Mars. Terraforming projects designed to thicken the atmosphere, warm the planet, and eventually make it habitable for Earth life. These aren't just science fiction concepts anymore. they're serious engineering proposals being studied by space agencies and private companies. If we can contemplate such projects with our current primitive technology, what might a civilization with millions of additional years of development have attempted? The irony is profound. We might be looking at a planet where ancient civilizations tried to do exactly what we're now planning to do, but in reverse. Instead of terraforming Mars to make it more habitable, they might have been trying to maintain its habitability as natural processes worked against them. Instead of adding atmosphere, they might have been desperately trying to prevent its loss. Instead of warming the planet, they might have been fighting a losing battle against inexorable cooling. The geological record of Mars preserves evidence of massive engineering projects that dwarf anything humans have ever attempted. Olympus Mons, the largest volcano in the solar system, shows signs of having been active far more recently than natural volcanic processes should allow. Could this represent attempts to maintain atmospheric pressure through artificial volcanic activity? The vast canyon system of Valles Marineris stretches across nearly a quarter of the planet's circumference. Could this be the remnant of a failed attempt to create artificial atmospheric circulation patterns? These speculations push the boundaries of what we can reasonably infer from current evidence, but they illustrate how different Mars looks when we consider the possibility of ancient intelligence. Features we've always attributed to natural geological processes take on new significance when viewed as potential artifacts of planetary-scale engineering. The timeline becomes even more intriguing when we consider what was happening on Earth during Mars's transition from habitable to frozen. This period coincides roughly with the emergence of complex life in Earth's oceans. The first multicellular organisms, the first complex ecosystems, the first hints of the biological complexity that would eventually lead to intelligence. Could this timing be coincidental, or does it represent a deeper connection between the two worlds? If Martian civilizations were facing environmental collapse, Earth would have appeared as the obvious refuge. A younger planet with a thicker atmosphere, stronger magnetic field, and increasingly stable climate. The logical destination for any species capable of interplanetary travel. But if they made that journey, where did they go? Why don't we find obvious traces of Martian colonization in Earth's early history? Perhaps we do, but we're not recognizing them for what they are. The sudden burst of biological innovation known as the Cambrian explosion remains one of the greatest mysteries in evolutionary biology. Life had existed on Earth for over 3 billion years, but it remained simple, mostly single-celled, and relatively unchanging. Then, in a geological instant, complex animals with shells, eyes, limbs, and sophisticated body plans appeared simultaneously across the globe. Traditional explanations focus on environmental changes that might have triggered this evolutionary burst, rising oxygen levels, changing ocean chemistry, or ecological interactions that suddenly favored complexity over simplicity. But these explanations struggle to account for the sheer speed and coordination of the changes. It's as if evolution suddenly acquired a blueprint for building complex organisms and implemented it simultaneously across multiple lineages. Could that blueprint have come from Mars? Not through directed colonization, but through the natural exchange of genetic material that we now know occurs between planets. Martian organisms, facing extinction as their world became uninhabitable, might have developed biological innovations at an accelerated pace. Some of these innovations could have been preserved in the rocks that regularly travel from Mars to Earth, then incorporated into terrestrial life through the horizontal gene transfer processes that are fundamental to microbial evolution. This scenario would explain several puzzling aspects of the Cambrian explosion. the simultaneous appearance of complex features across different lineages, the sophisticated biological structures that seem to require numerous coordinated genetic changes, the timing that coincides with Mars's transition from habitable to frozen. Instead of seeing the Cambrian explosion as a purely terrestrial event, we might be looking at the biological legacy of a dying world. The implications extend far beyond academic curiosity about ancient history. If Earth's biosphere really was enriched by genetic material from Mars, then we're not just studying another planet, we're studying our own deep ancestry. The DNA in our cells might carry information that first evolved under alien skies, shaped by environmental pressures we've never experienced, refined by evolutionary processes that played out on a world we've never seen. This possibility reframes the entire search for life in the universe. Instead of looking for biology that's completely alien to our own, we might be looking for distant relatives. Life that shares common ancestors, common biochemical pathways, common solutions to the fundamental challenges of existence. The universe becomes not a vast emptiness punctuated by rare islands of life, but an interconnected web where biological information flows between worlds, creating continuities across space and time that we're only beginning to understand. The search for evidence of ancient Martian civilizations is entering a new phase as our technology becomes sophisticated enough to detect increasingly subtle traces. Future Mars missions will carry instruments designed specifically to look for the kinds of chemical and isotopic signatures that might remain from industrial activity billions of years in the past. We're developing techniques to analyze mineral deposits, atmospheric chemistry, and even the magnetic properties of rocks with unprecedented precision. But even as our methods improve, we have to acknowledge the fundamental challenge we're facing. We're trying to reconstruct events that happened so long ago that most of the evidence has been erased by natural processes. It's like trying to read a book where most of the pages have been torn out. The remaining text has faded almost to invisibility, and the few words we can still make out are in a language we don't fully understand. This creates a profound epistemological problem. The absence of obvious evidence doesn't prove that ancient civilizations never existed on Mars, but the presence of ambiguous evidence doesn't prove that they did. We're operating in a realm where certainty may be impossible, where the best we can hope for is probability assessments based on incomplete data and tentative interpretations. Yet this uncertainty doesn't diminish the importance of the search. Even if we never find definitive proof of ancient Martian intelligence, the process of looking changes how we think about planetary evolution, the development of life, and the possibilities for intelligence elsewhere in the universe. Every anomaly we investigate, every unusual formation we study, every chemical signature we analyze adds to our understanding of how planets work and how life adapts to changing conditions. The search also forces us to confront uncomfortable questions about our own civilization's sustainability. If Mars really did host advanced societies that eventually vanished, what does that tell us about the long-term prospects for technological civilizations? Are there universal patterns in how intelligent species interact with their planetary environments? Are there thresholds that, once crossed, lead inevitably to collapse? The environmental history of Mars reads like a cautionary tale. A planet that started with conditions similar to early Earth, developed complex chemistry and possibly biology, then underwent rapid environmental changes that left it essentially sterile. The mechanisms that drove these changes, whether natural or artificial, operated on timescales that would have challenged even the most advanced civilizations to adapt? Could we be looking at our own future? Earth is currently experiencing rapid environmental changes driven by human industrial activity. Atmospheric chemistry is shifting, climate patterns are becoming unstable, and biological systems are showing signs of stress. The parallels with Mars' environmental history are disturbing, even if the specific mechanisms are different. But there's also reason for hope in the Martian story. If civilizations did exist on Mars and faced environmental collapse, some of their legacy appears to have survived. Not in the form of monuments or artifacts, but in the biological innovations that may have seeded Earth's own evolutionary explosion. Intelligence, once it emerges, might be more resilient than we assume. It finds ways to preserve itself, to pass on its innovations, to contribute to the ongoing story of consciousness in the universe, even when its original context disappears. The red planet hanging in our night sky becomes a symbol of both warning and promise. A reminder that civilizations are fragile and planetary environments can change rapidly, but also evidence that intelligence, once it emerges, leaves traces that can persist across geological time and even across the void of space. Mars might be silent now, but its story may not be over. It might continue in the questions we ask, the technologies we develop, and the biological heritage we carry in our very cells. As we prepare for human missions to Mars, we're not just exploring another world. We might be returning home to a planet where intelligence first stirred in our solar system, where the first minds wondered about their place in the cosmos, where the first civilizations faced the challenges of sustainability that we're now confronting ourselves. The search for ancient Martian intelligence is ultimately a search for understanding our own deeper story and our own cosmic significance. The story of Mars becomes even more intriguing when we examine the specific mechanisms by which ancient civilizations might have left their mark on the planet's geology. Unlike the obvious ruins we might expect from human archaeology, the signatures of truly ancient intelligence would be woven into the very fabric of the planet itself, expressed in ways that blur the line between natural processes and artificial intervention. Consider the phenomenon of rapid atmospheric loss that appears to have occurred on Mars. Traditional models suggest this should have been a gradual process, taking hundreds of millions of years as solar wind slowly stripped away the planet's protective envelope. But isotopic evidence points to much more dramatic changes happening over geological instants. Entire atmospheric compositions shifting in time frames that seem impossibly brief for natural processes alone. What if this rapid atmospheric loss wasn't entirely natural? What if it represents the signature of planetary engineering projects operating at scales we can barely comprehend? A civilization facing environmental collapse might attempt increasingly desperate measures to maintain habitability. Massive atmospheric processes, global-scale chemical interventions, or attempts to artificially maintain magnetic field strength through technological means. The failure of such projects would leave exactly the kind of signatures we're now finding in Martian rocks. Rapid isotopic shifts as artificial atmospheric compositions collapse back to natural equilibria. Unusual mineral concentrations, where industrial processes operated beyond sustainable limits. Chemical fingerprints of technologies pushed past their breaking points by civilizations fighting for survival against inexorable planetary change. This perspective transforms our understanding of what planetary death looks like. Instead of gradual cooling and atmospheric loss, we might be looking at the aftermath of technological civilizations that burned too bright, consumed too much, and ultimately accelerated the very environmental changes they were trying to prevent. The silence of Mars becomes not just the quiet of a world that never knew intelligence, but the profound stillness that follows civilizational collapse. Recent analysis of Martian soil samples has revealed another puzzling anomaly that fits this pattern. Concentrations of rare Earth elements that appear far too high for a planet that supposedly never experienced industrial activity. These elements are crucial for advanced electronics, energy storage systems, and the kind of sophisticated materials science that defines technological civilization. Their unusual abundance in certain Martian geological layers suggests extraction and processing operations that dwarf anything humans have ever attempted. The distribution of these element concentrations is particularly intriguing. They appear in patterns that correlate with some of the geometric formations visible from orbit, as if industrial sites were deliberately placed to optimize resource extraction and processing. The correlation isn't perfect, and alternative explanations involving unusual volcanic or meteoric processes can't be ruled out. But the statistical probability of such patterns arising purely by chance becomes increasingly difficult to defend. More disturbing are the signatures that suggest these industrial processes may have been operating right up until the environmental collapse that ended Mars' habitability. Instead of a gradual decline and abandonment of technology as conditions worsened, the evidence points to intensification of industrial activity during the planet's final habitable period. As if civilizations were desperately trying to engineer their way out of an environmental crisis, consuming ever more resources in a futile attempt to maintain the technological complexity their survival depended on. This pattern will be uncomfortably familiar to anyone watching our own civilization's response to environmental challenges. The tendency to double down on technological solutions, to increase consumption in the hope that growth will somehow solve the problems growth itself created. If Mars really did host civilizations that followed this path to its ultimate conclusion, then we're looking at a cautionary tale written in planetary geology. The magnetic properties of certain Martian rock formations provide another piece of this puzzle. Mars currently has almost no global magnetic field, but geological evidence suggests it once possessed a magnetic field as strong as Earth's. The loss of this field is usually attributed to the cooling and solidification of the planet's core, but the timeline doesn't quite match what we observe. Some regions of Mars show magnetic signatures that suggest the presence of powerful artificial magnetic fields operating long after the planet's natural magnetosphere should have disappeared. Geometric patterns of magnetic orientation that look more like the result of technological intervention than natural geological processes. Could these be the remains of attempts to artificially maintain planetary magnetic protection as the natural field weakened? The engineering challenges involved in such a project would be staggering even by our current standards. Creating artificial magnetic fields strong enough to protect an entire planet would require energy sources and materials science capabilities that push the boundaries of what we consider physically possible. Yet the alternative explanations for the magnetic anomalies we observe are equally challenging to conventional geological theory. Perhaps most intriguingly, some of these artificial magnetic signatures appear to have been operating in coordination with each other, as if they were part of a planet-wide system designed to maintain atmospheric protection through technological means. The geometric relationships between different magnetic anomaly sites suggest deliberate placement and coordination rather than random technological development. If such a system really existed, its ultimate failure would explain the rapid atmospheric loss that transformed Mars from habitable to frozen. Not gradual weakening of natural magnetic protection, but catastrophic failure of artificial systems that had been holding back environmental collapse through pure technological force. When those systems finally broke down, the accumulated environmental damage would have been released all at once, creating the kind of rapid planetary transformation that geological evidence suggests actually occurred. The implications of this scenario extend far beyond Mars itself. It suggests that technological civilizations may face a fundamental trap as they develop. The more advanced their technology becomes, the more dependent they become on maintaining that technology to survive in environments they've altered beyond natural sustainability. The failure of critical systems doesn't just mean inconvenience or economic disruption, it means civilizational collapse on a planetary scale. This dynamic helps explain one of the most puzzling aspects of the search for extraterrestrial intelligence. If technological civilizations are common in the universe, why don't we see obvious evidence of their activities? Why aren't the skies filled with radio signals, the planets covered with visible infrastructure, the asteroid belts stripped bare by industrial mining operations? The Martian example suggests a possible answer. Technological civilizations may be inherently unstable, lasting only brief periods on cosmic timescales before environmental or systemic collapse erases their presence from the observable universe. What we're looking for when we search for alien intelligence may not be thriving civilizations, but the subtle archaeological traces of societies that rose, flourished briefly, and then vanished into planetary geology. This perspective reframes the entire search for extraterrestrial intelligence from an optimistic quest for cosmic companions to a more sobering archaeological investigation of civilizational failure. Every planet becomes a potential archaeological site. Every unusual geological formation becomes a possible monument to vanished intelligence. Every chemical anomaly becomes a potential signature of industrial processes that once operated under alien skies. The search techniques being developed to investigate ancient Martian intelligence are already being applied to other worlds in our solar system. The moons of Jupiter and Saturn show their own puzzling anomalies that could represent either exotic natural processes or the remains of technological activity. Europa's subsurface ocean contains chemical signatures that don't quite match our models of natural ocean chemistry. Titan's atmospheric composition includes compounds that are difficult to explain through purely natural processes. Even more intriguingly, some of these chemical signatures appear to be changing over time in ways that suggest ongoing processes rather than ancient remains. Could we be looking at ecosystems or even civilizations that are still active beneath the ice shells of distant moons? Or are we seeing the slow decay of artificial systems that have been running autonomously for millions of years after their creators disappeared? The technology being developed to answer these questions is pushing the boundaries of what's possible in remote sensing and chemical analysis. Instruments capable of detecting individual molecules and atmospheric samples taken from millions of miles away. Radar systems that can penetrate kilometers of ice to map subsurface structures in unprecedented detail. Magnetic field sensors sensitive enough to detect the faintest traces of artificial electromagnetic activity. As these technologies mature, they're revealing a solar system that's far stranger and more complex than we ever imagined. Instead of a collection of dead worlds orbiting a single living planet, we're seeing an interconnected system where chemical and biological processes link worlds across the vast emptiness of space. Where the history of one planet influences the development of others through mechanisms we're only beginning to understand. the discovery of organic compounds in the plumes of Enceladus, the detection of seasonal methane variations in Mars' atmosphere, the identification of possible biosignatures in Venus's upper atmosphere. All of these findings point to a solar system where life and possibly intelligence have been far more widespread than traditional models predicted. We're not looking for rare exceptions to cosmic sterility, but for the current state of processes that have been operating throughout the history of our planetary neighborhood. This realization transforms our understanding of what it means to search for life elsewhere in the universe. Instead of looking for Earth-like planets orbiting Sun-like stars, we should be investigating the archaeological record of our own solar system. Instead of building ever more powerful telescopes to peer across interstellar distances, we should be developing ever more sensitive instruments to decode the chemical and geological signatures preserved in the worlds around us. The ancient civilizations we're seeking may not be in distant galaxies. They may be encoded in the rocks beneath our feet, the meteorites in our museums, and the atmospheric chemistry of planets we can reach with current technology. The greatest archaeological discovery in human history may not require interstellar travel. It may only require learning to read the stories written in planetary geology by intelligence that preceded us by millions or billions of years. As we prepare to become a multiplanetary species ourselves, understanding these ancient stories becomes crucial for our own survival. The environmental challenges that may have destroyed Martian civilizations are not unique to Mars. They represent universal consequences of technological development that any advanced civilization must eventually face. Learning from the successes and failures of those who came before us may be the key to avoiding their fate. The red planet in our night sky becomes not just a destination for future exploration, but a library of civilizational experience, a repository of hard-won knowledge about the challenges of maintaining technological societies on planetary scales, a testament to both the power and the fragility of intelligence in a universe that doesn't guarantee survival to any species, no matter how advanced. Every mission to Mars, every sample returned, every measurement taken brings us closer to understanding not just what happened on that distant world, but what might happen to our own. The search for ancient Martian intelligence is ultimately a search for wisdom that could determine whether human civilization becomes another brief chapter in the geological record, or whether we can learn from the mistakes of our predecessors and forge a more sustainable path forward. The story written in Martian stones may be the most important book our species ever learns to read. Because in deciphering the fate of those who came before us, we may discover the keys to ensuring that our own story continues far beyond the brief moment we currently occupy in cosmic history. The silence of Mars speaks volumes, if only we learn how to listen. As we stand at the threshold of becoming an interplanetary species ourselves, the lessons hidden in Mars' geological record take on urgent practical significance. The environmental collapse that may have claimed ancient Martian civilizations didn't happen in isolation. It followed patterns that we can now recognize in our own planetary systems, patterns that suggest certain trajectories of technological development may be inherently unsustainable. The atmospheric chemistry of ancient Mars tells a story of rapid, cascading changes that accelerated once critical thresholds were crossed. Greenhouse gas concentrations that spiked suddenly before crashing. Ocean chemistry that shifted from stable to toxic in geological instants. Magnetic field fluctuations that suggest desperate attempts to maintain planetary protection through artificial means. These patterns are eerily familiar to anyone studying Earth's current environmental trajectory. We're seeing similar threshold effects in our own climate systems. Similar feedback loops where technological solutions to environmental problems create new environmental problems that require even more intensive technological intervention. Similar dependencies on complex systems that become more fragile as they become more essential to civilizational survival. But there's a crucial difference in our situation. We have the advantage of being able to study what happened on Mars. We can potentially learn from mistakes that cost another world its habitability. The question is whether we're wise enough to recognize the warnings and humble enough to change course before we repeat the same errors. The search for ancient Martian intelligence is revealing something profound about the nature of technological development itself. Advanced civilizations don't just alter their immediate environment. They reshape the fundamental physics and chemistry of their planetary systems. They become geological forces comparable to volcanoes, asteroids, or climate cycles. And once they reach that level of planetary influence, their survival becomes intimately connected to their ability to manage systems of almost incomprehensible complexity. This creates what researchers are beginning to call the technological trap. The more successful a civilization becomes at controlling its environment, the more dependent it becomes on maintaining that control. Natural resilience gets replaced by technological resilience. Biological adaptation gets supplanted by engineered solutions. The civilization becomes like a rider on a bicycle, stable only as long as it keeps moving forward, but catastrophically vulnerable to any disruption that stops the forward momentum. The geological record of Mars suggests this is exactly what happened there. Instead of finding evidence of gradual decline and graceful adaptation to changing conditions, we see signatures of systems pushed to their absolute limits, then failing catastrophically when those limits were exceeded. Industrial processes operating at maximum capacity right up until the moment they stopped forever. Atmospheric management systems running at unsustainable energy expenditures until they collapsed and took the entire planetary environment with them. The mineral deposits left behind by these processes tell their own story. Rare earth elements concentrated far beyond natural abundance, then abruptly cut off as if extraction suddenly ceased. Isotopic signatures of nuclear processes operating at industrial scales, then ending with the kind of abrupt termination that suggests systemic failure rather than planned shutdown. Chemical traces of synthetic materials that required enormous energy inputs to create, preserved in geological layers like fossils of a technological ecosystem that consumed itself. Perhaps most telling are the magnetic anomalies that appear to represent the remains of planetary-scale engineering projects. These weren't small-scale interventions or local modifications. They were attempts to artificially maintain the fundamental physical processes that keep planets habitable. Magnetic field generation on a scale that would dwarf our largest power plants. Atmospheric processes that would make our most ambitious geoengineering proposals look like backyard science projects. The failure of these systems would have been swift and absolute. When technological civilization becomes the primary life support system for an entire planet, the collapse of that civilization means the collapse of planetary habitability itself. There's no graceful degradation, no gradual return to natural equilibrium. There's only the kind of rapid environmental transformation that turns a living world into a frozen wasteland in geological minutes. This dynamic explains why the search for extraterrestrial intelligence has been so frustratingly quiet. If technological civilizations typically follow this pattern of rapid growth, planetary transformation, and catastrophic collapse, then the universe would be full of worlds like Mars, planets that once hosted advanced intelligence, but now show only the faintest archaeological traces of their former inhabitants. The implications for our own civilization are sobering. We're currently following a trajectory that looks remarkably similar to what the Martian evidence suggests happened there. Exponential growth in energy consumption, increasing dependence on technological systems for basic survival, rapid alteration of planetary chemistry faster than natural systems can adapt, growing complexity in the technological infrastructure that supports modern civilization. But recognition of these patterns also provides opportunities for different choices. Unlike hypothetical Martian civilizations, we have the advantage of being able to study their fate before experiencing it ourselves. We can potentially identify the critical thresholds and feedback loops that led to their collapse and design our own development to avoid triggering the same cascading failures. The key insight emerging from Mars research is that sustainability isn't just about using renewable energy or reducing pollution. It's about maintaining the kind of planetary resilience that allows civilizations to survive the inevitable disruptions that affect all complex systems. This means preserving natural processes alongside technological ones, maintaining biological diversity as insurance against technological failure, developing distributed rather than centralized systems that can degrade gracefully rather than failing catastrophically. The ancient Martian civilizations may have been far more advanced than us in terms of pure technological capability. Their ability to manipulate planetary magnetic fields and atmospheric chemistry suggests engineering prowess that we're still centuries away from achieving. But their apparent inability to maintain sustainable relationships with their planetary environment ultimately led to their extinction. Our challenge is to achieve technological advancement without falling into the same trap of increasing complexity and decreasing resilience that seems to have claimed Mars. This requires a fundamentally different approach to progress, one that measures success not just by what we can build or control, but by what we can preserve and sustain over geological timescales. The search for traces of ancient Martian intelligence is entering its most sophisticated phase, as new analytical techniques allow us to detect increasingly subtle signatures of past technological activity. Spectroscopic analysis of Martian atmospheric samples can now identify individual molecular species at concentrations measured in parts per trillion. Magnetic field mapping has achieved resolution that can detect artificial magnetic structures smaller than city blocks from orbital distances. These enhanced capabilities are revealing new layers of complexity in Mars's geological record. Chemical signatures that appear and disappear in patterns too regular to be entirely natural. Isotopic ratios that suggest nuclear processes operating under controlled conditions rather than random natural decay. Mineral formations with crystalline structures that require the kind of precise temperature and pressure control that only advanced materials science could provide. Each new discovery adds another piece to a puzzle that's simultaneously becoming clearer and more mysterious. The evidence for some kind of advanced activity on ancient Mars continues to accumulate, but it remains frustratingly indirect. We're like detectives investigating a crime scene where the perpetrator was extraordinarily careful to clean up after themselves, leaving only the most subtle traces for us to discover millions of years later. The challenge is compounded by the fact that we don't really know what we're looking for. Our expectations about what ancient technology should look like are inevitably shaped by our own technological development. We assume advanced civilizations would use metals, electronics, and energy sources similar to our own. But a civilization that developed along different paths might have created technologies so alien to our experience that we literally wouldn't recognize them as artificial. This is why some researchers are focusing less on identifying specific artifacts and more on detecting patterns that suggest intelligent design rather than natural processes. Statistical analysis of geological formations looking for regularities that would be extremely improbable if they arose through random natural events. Mathematical relationships between different types of anomalies that suggest coordinated rather than independent causes. The results of these analyses are tantalizing but inconclusive. There do appear to be correlations and patterns in the Martian data that are difficult to explain through known natural processes. But proving that these patterns result from ancient intelligence rather than natural phenomena we don't yet understand remains elusive. The search is also expanding beyond Mars itself to include the broader context of our solar system's development. If Mars really did host advanced civilizations, their activities might have left traces on other worlds as well. Asteroid mining operations could have altered the composition of the asteroid belt. Interplanetary transportation systems might have left debris in stable orbital zones. Even failed colonization attempts on other worlds might have left archaeological signatures we could detect with sufficiently sensitive instruments. Some of the most intriguing evidence is coming from analysis of meteorites that originated not just from Mars, but from asteroids and possibly other planetary bodies. These samples represent a kind of natural archaeological collection, preserving materials from throughout the solar system's history in forms that have been protected from ongoing geological processes. Several meteorite samples contain mineral phases that appear to have formed under conditions that don't match any known natural processes. Crystalline structures that require precisely controlled cooling rates. Isotopic compositions that suggest artificial enrichment of specific elements. Even more puzzling, some of these anomalous minerals appear in multiple meteorites from different source bodies, suggesting that whatever processes created them operated on a system-wide scale. The possibility that we're looking at evidence of solar system-wide technological activity in the ancient past is both thrilling and terrifying. Thrilling because it would confirm that intelligence has indeed emerged before in our cosmic neighborhood. Terrifying because it would also confirm that even civilizations capable of operating on interplanetary scales eventually succumb to forces that erase them from the historical record. This perspective transforms our understanding of what human space exploration really represents. We're not just expanding into empty wilderness. We might be retracing paths first explored by intelligence that preceded us by hundreds of millions of years. Every asteroid we visit, every planet we study, every moon we investigate, might contain archaeological evidence of civilizations that once asked the same questions we're asking now about their place in the universe. The search for ancient intelligence is also revealing new possibilities for how such civilizations might have tried to preserve themselves or their knowledge for future discovery. If they recognized that their physical presence was unlikely to survive geological timescales, they might have encoded information in more durable forms. Crystalline structures that could preserve complex information for billions of years. Genetic modifications to simple organisms that could carry artificial DNA sequences forward through natural evolutionary processes. Even modifications to the orbits of asteroids or small moons that would create artificial patterns detectable to future astronomers. The idea that ancient civilizations might have left us messages encoded in the very structure of our solar system sounds like science fiction, but it's based on solid physical principles. Information can be stored in remarkably durable forms if you have the technology to manipulate matter at atomic scales. And some of the orbital relationships between objects in our solar system do show mathematical regularities that are statistically unlikely to have arisen through natural processes alone. Whether these patterns represent messages from ancient intelligence or simply reflect natural gravitational processes we don't fully understand remains an open question. But the fact that we can even ask such questions seriously demonstrates how profoundly the search for ancient Martian civilizations is expanding our conception of what's possible in cosmic history. As we prepare to establish our own permanent presence on Mars, we're not just becoming an interplanetary species. We might be returning to a world where intelligence first emerged in our solar system, where the first minds contemplated the stars and wondered if they were alone, where the first civilizations faced the challenges of planetary stewardship that we're now confronting ourselves. The irony is that we might be better positioned to learn from ancient Martian mistakes than they were to avoid making them in the first place. They faced environmental challenges without the benefit of studying previous civilizational collapses. We have their example, encoded in planetary geology, to guide our own choices about sustainable development and technological wisdom. The search for ancient intelligence on Mars is ultimately a search for the kind of deep time perspective that could help our own civilization develop the wisdom necessary for long-term survival. Every chemical signature we decode, every anomalous formation we investigate, every piece of the ancient puzzle we recover brings us closer to understanding not just what happened on Mars, but what we need to do differently to ensure our own story continues far into the cosmic future. The red world hanging in our night sky may be silent now, but it might still have the most important lessons to teach us about the relationship between intelligence, technology, and planetary survival. Learning. To hear those lessons could be the key to ensuring that human civilization becomes not another cautionary tale written in geological strata, but a success story that spans the stars. The implications of finding ourselves potentially connected to this ancient Martian legacy extend into territories that challenge our most fundamental assumptions about evolution itself. If life really did travel between Mars and Earth during the critical periods when both worlds were developing complex ecosystems, then evolution isn't just a planetary process. It becomes something far more dynamic and interconnected, a cosmic phenomenon where biological innovations developed under alien conditions can seed entirely different evolutionary pathways on distant worlds. This perspective revolutionizes how we think about the development of intelligence throughout the universe. Instead of viewing consciousness as a rare accident that happened once on Earth, we might be looking at a recurring pattern where intelligence emerges, spreads its influence across multiple worlds, and then persists in forms we. They're only beginning to recognize the biological complexity that eventually gave rise to human consciousness, might carry within it the accumulated evolutionary wisdom of multiple worlds, multiple environments, multiple experiments in what it means to be alive and aware. The genetic code that defines every living thing on Earth becomes a potential archaeological record, stretching back not just to the origins of terrestrial life, but possibly to the origins of life in our entire solar system. Hidden within the DNA sequences that govern our cellular processes might be information that first evolved under Martian skies, shaped by environmental pressures we've never experienced, refined by evolutionary processes that played out on a world we're only now learning to explore. This possibility transforms the entire field of genetics into a form of interplanetary archaeology. Every unusual gene sequence, every evolutionary innovation that seems to appear suddenly in the fossil record, every biological structure that requires complex coordinated changes becomes a potential clue to our deeper cosmic heritage. We might be carrying within our own cells the biological legacy of civilizations that faced and perhaps solved challenges we're only beginning to encounter. The timing of major evolutionary transitions on Earth takes on new significance when viewed through this lens. The emergence of complex cells, the development of multicellular life, the sudden appearance of sophisticated biological structures during the Cambrian explosion, all of these crucial steps in the development of terrestrial life coincide roughly with periods when Mars was experiencing its own dramatic environmental changes. Could these evolutionary leaps represent the integration of biological innovations that first developed on Mars as that planet's ecosystems faced increasing environmental stress? Could the creativity and adaptability that defines terrestrial life be the result of incorporating survival strategies developed by organisms that had to adapt to rapidly changing conditions on a dying world? This scenario would explain some of the most puzzling aspects of Earth's evolutionary history. The speed with which complex biological structures appeared, the seemingly coordinated nature of evolutionary changes across different lineages, the appearance of biological innovations that seem to require numerous simultaneous genetic modifications, instead of these features arising independently through random processes, they might represent the importation of evolutionary solutions that had already been developed and tested under different environmental conditions. The implications extend beyond biology into the realm of consciousness itself. If the neural structures that eventually gave rise to human intelligence carry genetic information that originated on Mars, then our capacity for thought, creativity, and self-awareness might have roots that stretch back to minds that first contemplated existence under alien stars. The questions that drive human curiosity, our compulsion to explore and understand the universe around us, our sense of wonder. When we look up at the night sky, all of these defining characteristics of human consciousness might echo neural patterns that first evolved in response to very different environments on a very different world. We might be experiencing emotions, thoughts, and drives that were shaped by evolutionary pressures we've never faced, inherited from ancestors who lived and died under skies we've never seen. This possibility reframes our entire relationship with Mars, from scientific curiosity about another planet to something approaching a homecoming. Every mission we send to the red planet, every sample we collect, every measurement we take might be bringing us closer to understanding not just another world, but our own deepest origins and the source of the very consciousness that drives us to ask these questions in the first place. The search for traces of ancient Martian intelligence becomes a search for our own cosmic genealogy. We're not just looking for evidence of other minds that might have existed in our solar system. We might be looking for evidence of the minds that gave rise to our own capacity for thought and wonder. Recent advances in genetic archaeology are beginning to provide tools that might allow us to detect these kinds of ancient biological influences. Techniques for tracing the evolutionary history of specific gene sequences back through deep time. Methods for identifying genetic innovations that appear suddenly in the evolutionary record without clear terrestrial predecessors. Approaches for detecting the kind of horizontal gene transfer events that could have incorporated extraterrestrial biological information into terrestrial evolutionary processes. The results of these investigations are still preliminary, but they're revealing some intriguing patterns. Certain gene sequences that are crucial for neural development appear to have no clear evolutionary precursors in earlier terrestrial life forms. They seem to appear suddenly in the evolutionary record, already fully formed and functional, as if they were imported from somewhere else rather than gradually evolved from simpler predecessors. Other genetic innovations show signs of having been optimized for environmental conditions that don't match anything that existed on early Earth. Stress response mechanisms that seem designed for higher radiation environments. Cellular repair systems that are optimized for the kind of oxidative stress that would be common on a planet with a thinner atmosphere. Metabolic pathways that seem almost over-engineered for terrestrial conditions, as if they were designed for more challenging environments. These patterns don't prove that terrestrial life incorporated genetic material from Mars, but they're consistent with what we might expect to find if such transfers had occurred. They suggest that at least some of the biological innovations that define terrestrial life might have originated under conditions very different from those that existed on early Earth. The possibility becomes even more intriguing when we consider what we know about the environmental conditions that existed on Mars during the periods when these genetic innovations were appearing on Earth. Mars was experiencing exactly the kind of environmental stress that would drive rapid evolutionary innovation. Increasing radiation as the magnetic field weakened, atmospheric changes that would require new metabolic strategies, temperature fluctuations that would demand enhanced cellular repair mechanisms. Organisms facing these challenges would have been under intense evolutionary pressure to develop exactly the kinds of biological innovations that appear suddenly in Earth's evolutionary record. If some of these innovations were preserved in rocks that travelled from Mars to Earth, and if they were incorporated into terrestrial life through natural genetic exchange processes, it would explain both the timing and the nature of some of Earth's most important evolutionary transitions. This scenario also provides a framework for understanding some of the more puzzling aspects of human consciousness itself. The human brain is remarkably overbuilt for the challenges our survival species actually faced during its evolutionary development. We have cognitive capabilities that far exceed what would be necessary for hunting, gathering, and basic social cooperation on the African savanna. Our capacity for abstract mathematics, artistic expression, philosophical contemplation, and scientific reasoning seems almost disproportionate to the environmental pressures that shaped human evolution. It's as if our brains were designed for challenges more complex than those our species actually encountered during its development on Earth. If human neural development incorporated genetic innovations that originally evolved in response to the challenges faced by intelligent life on Mars, it would explain this apparent mismatch. Our cognitive abilities might reflect adaptations to environmental and civilizational challenges that our species never directly experienced, but that our genetic heritage carries forward from ancestors who lived and thought under very different conditions. The creativity that drives human art and science, our compulsion to explore and understand, our ability to imagine possibilities beyond our immediate experience, all of these defining characteristics of human consciousness might be evolutionary adaptations to the challenges of maintaining technological civilization on a planet undergoing environmental collapse. In this view, human civilization represents not the first attempt at technological development in our solar system, but a continuation of processes that began long ago on Mars. We're not starting from scratch in our attempts to build sustainable relationships with our planetary environment. We might be working from a genetic and psychological foundation that was shaped by previous attempts to solve similar problems under even more challenging conditions. The environmental challenges we're currently facing on Earth, from climate change to resource depletion to the complexities of managing technological systems at planetary scales, might be triggering response patterns that evolved originally as solutions to similar challenges faced by Martian civilizations. Our drive to develop renewable energy, our growing awareness of ecological interconnectedness, our emerging understanding of planetary boundaries, all of these might reflect the activation of cognitive and social patterns that were first developed by minds that faced environmental collapse on another world. This possibility transforms our current environmental crisis from an unprecedented challenge into a familiar pattern that consciousness has encountered before. Instead of being the first intelligent species to face the consequences of planetary-scale technological development, we might be drawing on evolutionary wisdom developed by civilizations that grappled with similar problems millions or billions of years ago. The genetic and neural heritage we might carry from Mars could provide us with cognitive tools for solving sustainability challenges that purely terrestrial evolution might never have developed. Our ability to think in planetary timescales, to understand complex system interactions, to imagine technological solutions to environmental problems, might all reflect mental capabilities that were originally shaped by the necessity of maintaining civilization on a dying world. But this heritage also carries warnings. If our cognitive patterns really do reflect adaptations to civilizational challenge and environmental collapse, then we might also carry within us the psychological and social dynamics that contributed to the failure of previous attempts at sustainable technological development. The same drives that push us toward technological innovation might also carry the seeds of the kind of overconfidence and environmental blindness that led to the collapse of whatever civilizations might have existed on Mars. Understanding this dual heritage becomes crucial for our own survival. We need to learn to activate the problem-solving and adaptive capabilities that our cosmic evolutionary history might have given us, while avoiding the patterns of thinking and behavior that led to the destruction of the civilizations that gave rise to those capabilities in the first place. The search for evidence of ancient Martian intelligence thus becomes not just an archaeological investigation, but a crucial component of understanding our own psychological and civilizational inheritance. Every piece of evidence we find, every pattern we detect, every anomaly we investigate, might provide insights not just into what happened on Mars, but into the deepest structures of human consciousness and the civilizational patterns we're currently enacting on Earth. The red planet in our night sky becomes a mirror, reflecting back at us possibilities and warnings that are encoded in our own genetic and psychological heritage. Understanding what happened there might be the key to understanding what's happening here and what we need to do differently to ensure that our own story continues far beyond the brief moment we currently occupy in cosmic history. As we prepare to return to Mars, we might not just be exploring another planet. We might be returning to the source of our own deepest cognitive and civilizational patterns, seeking to understand the origins of our own consciousness and the cosmic heritage that shapes every thought we think and every choice we make about our relationship with the planetary environment that sustains us. So here we stand, staring up at that red dot in the darkness, carrying questions that might reshape everything we thought we knew about intelligence, consciousness, and our place in cosmic history. The possibility that Mars once hosted advanced civilizations isn't just about discovering ruins or artifacts on another world. It's about recognizing that we might be part of a story that began long before Earth ever knew the stirrings of complex life. Every piece of evidence we've explored, from chemical anomalies in ancient rocks to the mysterious timing of evolutionary leaps on our own planet, points toward a universe where intelligence isn't rare or accidental, but recurring and resilient, where consciousness finds ways to preserve itself across geological time and interplanetary distances, where the questions we ask and the drives that push us to explore might echo thoughts that first formed under alien skies. Whether we ever find definitive proof of ancient Martian civilizations or not, the search itself is changing us. It's forcing us to think in deeper timescales, to consider our own fragility and potential, to recognize that the environmental challenges we face today might be part of patterns that consciousness has encountered before. The red planet offers us both warning and wisdom if we're humble enough to listen. As we prepare to become an interplanetary species ourselves, we're not just taking humanity to the stars. We might be continuing a cosmic conversation that began billions of years ago, carrying forward the curiosity and creativity that first emerged when intelligence looked up at the night sky and wondered if it was alone. The silence of Mars might not be an ending, but a pause, waiting for the next chapter in a story that's far older and more magnificent than we ever dared imagine.